Let's get started. So the whole focus of the next section is just the mean value theorem, and it makes very intuitive sense. So we'll go over big picture what the whole section's about, then get into the nitty-gritty. So imagine I have some function f on the closed interval a, b, and I know it's continuous on that interval, and I know it's differentiable on the interval open a, b. So not necessarily differentiable at those points, because the function could or could not end there, but it is differentiable on every point in between those. You with me so far on what this function is? So if you look at this point of the function, so that's the point a comma f of a, and you look at this point on the function, that's b comma f of b, what is the average slope of the function on this interval?
Be at the midpoint. That'd be
The average slope of the function from here to here, you just do rise over run. Nothing tricky. It's just f of b minus f of a over b minus a. That's all it is. We call that the average slope. All the mean value theorem says is that if you have a function that's continuous on the closed interval and differentiable on the open interval, then there exists some point between a and b, call it x naught, such that the derivative at that point, the slope at that point, is the same as the average slope from this point to this point. Or in other words, there exists some point x naught such that the derivative at x naught is equal to f of b minus f of a over b minus a. And it's pretty intuitive, because to get my function from here to here, I could either go straight there, then my function is obviously always the average slope. But now notice my function starts out above the average slope, so my derivative is bigger, 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 bigger. Well, it eventually has to get smaller, smaller, smaller to get back to that point. Or if I would have come down this way and start out with a negative derivative, come down like this, well, I got to get back to that point, so eventually I got to curve back up. And in that process of curving back up, my derivative at some point is going to be exactly parallel to that line. Make sense? Mean value theorem. So that's the gist of what the whole section's about. We'll work our way up to that proof, and then prove a couple things that follow directly from it. So, first lemma. If f is a function, so we'll prove it over here. Proof of lemma, well, I'll just write whatever we're proving. No, I'll just say proof lemma 46 and just get started. 1, let f be a function on the closed interval a, b to r. Let f be continuous. And on a, b,
I think you're proving that theorem right below.
differentiable. Am I looking at the wrong one? I'm supposed to be looking up here. Yep, thank you. Restart. Let f be a function. Anytime I use an I, that's an open interval. So let f be a function from an open interval I to r. Let f from I to r such that f prime at x naught exists and x naught is maximizer. Ooh. Do you remember what a maximizer for a function is?
It gives you the f of x is the max element.
Right. X naught is a maximizer if and only if f of x naught is the max element in the range. Exactly what you would think.
Aren't we using it?
If we're looking at this function, the maximizer is this point because there's the max. Okay. Now we need to think back. I should have went and found where the theorem is. We already proved a theorem that if you define a function on an interval, then it achieves a min and a max on that interval. On a closed interval.
Yeah, on a closed interval.
That has to be on a closed interval. if I wrote that wrong. Now, I be a neighborhood of x naught. Oh, I don't need to use the fact that this achieves a max or a min because x naught is already my maximizer. Okay, it's given to me. I was wondering how the heck I was going to get my maximizer. It's given to me in the problem. Sorry. Okay, so I know that x naught is a maximizer of this function. I'm trying to prove that the derivative at x naught is 0. So in other words, when we look at this function, obviously we have a max here. We're proving that the derivative at the max, the slope at the max of a function is 0. And it's the same proof, we're not going to do it for the minimizer, and the minimizer, the derivative at that point is 0. So at the max and the min, the slope is 0, so the derivative is 0, that's what we're proving. So let this thing be a maximizer. And I know that f prime of x naught exists. So observe that f prime of x naught can be written as the limit as x approaches x naught, where we only use values to the left of x naught, of f of x minus f of x naught all over x minus x naught. Now let's see what I know. So I know that x is always less than x naught when I take this limit, right?
Why do we do that?
Why what?
Why are we using only values left of x naught?
We're going to use values left. You'll see why I restrict it here, but there's no reason that I can't, right? Any sequence that converges now has to converge to this value because this is defined. If I could find two different sequences that converge to it, giving two different values, then the derivative doesn't exist. Right? So, since I know that the derivative exists, I know that this limit gives me the derivative, even if I restrict it to coming at it from the left-hand side. Now, since x is always less than x naught, then the denominator is always positive.
Would that need to be less than or equal to? Because what if you're...
You don't do equal when you take the limit as you approach.
Sorry, it's an open arrow. I'm sorry.
Well, also, remember that by definition, the limit as x approaches x naught, we never use x naught.
Right.
So,
right.
Okay. So now, notice that x minus x naught is always a negative number. I said positive before, negative number. This is always a negative number. And notice f of x minus f of x naught is always a negative number. This is the max value. This is the maximizer, so this has to be the max value. So f of x is always less than or equal to f of x naught. So this is always negative or 0, and this is always negative. In either case, this is always less than or equal to 0. So observe that, and that f prime of x naught is also equal to the limit as x approaches x naught, where we always use values to the right of x naught. That's still a perfectly valid way to do it. I can approach it from the right or from the left. So then, that gives me that f of x minus f of x naught over x minus x naught, in this case, is always going to be greater than or equal to 0.
How did you get less than or equal to 0 on the top one? If both the denominator and numerator are negative, then isn't it positive?
This could have been 0, negative and negative or 0.
So it'd be greater than or equal to 0.
If I had a sine function, then I could have found a point to the left that gives me the same height as I get on my maximizer, because they're all maximizers. You can have multiple maximums in your range.
Yes, you're saying the numerator is either negative or 0?
Yes.
And then the denominator is
always
negative.
negative.
Oh, thank you. Wait. Oh yeah, so greater than or equal to 0. Okay. A negative divided by a negative, or a 0 divided by a negative.
Right.
In either case, 0. Thank you. And then, yes, so then I did this one backwards. So let's make sure that makes sense now. Now if x is greater than x naught, this is always positive, but now this is always negative or 0 still. So this is always positive, this is always negative or 0. In either case, we either get a negative number or we get 0. Make sense? Therefore, f prime at x naught is equal to 0. We know that f prime at x naught is greater than or equal to 0, and we know it's less than or equal to 0. The only way to satisfy both those is if it's 0. And we're done. Any questions on that one? Okay, let's move on to the next one. Proof of Theorem 4.17. So 1, now I do the big let I started before. So let f be a function whose domain is a closed bounded interval to R such that, now I know that this thing's going to achieve a max and a min. I bet that's what I may have to use. Anyways, I'll let f from, such that f is continuous and on the open interval AB is differentiable. Comma, and such that, we require a lot of information from this thing, and such that f of A is equal to f of B. Okay, let's go over the picture of what we're going to prove here and then come back to it. Okay, so here's what we're doing on this one. So now I've got a function defined on the closed interval from A to B. I don't know anything about it, except for that it's continuous and then differentiable on the interior. Now, and such that f of A is equal to f of B. All that makes sense. Okay, so that now I'm going to prove that then there has to be a point x naught somewhere in here such that the derivative at that point is 0. So either right here or right here is the way we could pick either of those for our x naught with the picture that I've drawn. But one of two cases is going to happen. Either the function has some maximums and minimums somewhere in between, or it's a constant function. If it's a constant function, the derivative is going to be 0. We'll handle that case. And then if it's not a constant function, then we already know since it's defined on a closed bounded interval, it has to achieve a max and a min. Somewhere that's not these endpoints. If it achieves a max and a min at those endpoints, it's a constant function. Otherwise, it has to achieve them somewhere that's not those points.
Now do you know it has max and min?
Every continuous function defined on a closed bounded interval achieves a maximum and a minimum. Yeah, I should have found where that theorem was from last time, but that's one that we already have from chapter 3.
Right.
So that's what we're using there. So in this case, it doesn't matter. We don't even need to use the fact that it achieves a maximum and a minimum. We just need that it achieves a max and we're done. So the derivative would also be 0 at a minimum, but we just need to do it at a max. So since f is continuous, there exists x naught in the closed interval AB such that x naught is maximizer. Continuous function defined on a closed bounded interval achieves a max somewhere. Might be the endpoints, might be somewhere in between. We'll handle both those cases. If x naught is equal to A or x naught is equal to B, then
Well, you know that
then f of x is equal to a constant, which gives me that f prime of x is equal to 0.
if x naught is equal to A, then is it also not equal to B?
if it's equal to A, if x naught is equal to A or B, if that happened to be the point that we chose as our maximizer, so up here we randomly grab a point x naught that we know is a maximizer. That's all we know about it. Well, we could have accidentally grabbed one of these 2 points. If it was one of these 2 points, then every point in the function is a maximizer. We're talking about a constant function. So then the derivative is 0 everywhere for the function, and so there exists a point somewhere in between A and B that gives us a derivative of 0. Notice I need to find a point between A and B that gives me a derivative of 0. Doesn't count if I show it at A or B. And I know that, I also know that I can't even take the derivative at A or B necessarily. So f prime is equal to that for all x in the open interval AB. That's a better way to say it. Because that's the only place where I know I have a derivative, right? This thing's only differentiable on this interval.
I still don't understand how x not being A or B gives you a constant function. Like, what if it just had your 2 points and a slope down in between them?
Oh shoot. Yep, it achieves a max and a min. We have to use both. Good catch. Yep. Since f naught is continuous, then there exists, we'll call them x1 and x2, x1 and x2 such that x1 is a maximizer and x2 is a minimizer. Okay, 3. Now, if our max and min, there we go, are the points A and B, then it's a constant function, and there's a point in the middle whose derivative is 0.
Couldn't you just say if x1 equals x2? Rather than if x1 is equal to A and x2 is equal to
I could, but all I need to do is handle the case with A's and B's so I can get those out of the way, because they're my endpoints. So I know how to handle this when I don't have to worry about A and B, so I just need the case, handle A and B, okay, now get that out of the way. Otherwise, we'll be good. Okay, so if our maximizer and minimizer are AB, comma, then f of x is a constant function. And so f prime of x is equal to 0 for all x in the open interval. Otherwise, what the heck did I just write? Otherwise, comma, let x naught be the maximizer slash minimizer that's not A or B. So if A and B are my maximizer or minimizer, then the whole thing is a constant function and we're done. Otherwise, if at least one of them isn't a maximizer or a minimizer, then let x naught be that point. So all I know about x naught is it's a maximizer or a minimizer. And it can't be A or B, so it has to be some point in between. Make sense? Then x naught is in the open interval A, B, and f prime of x naught is equal to 0 by lemma, whatever lemma we just used. And we're done. Right? the lemma we did here is we proved that the derivative at a maximizer or minimizer is 0.
Oh, right.
What are we trying to prove here? We're trying to prove, look, if you got a function like this, then there's some point in the middle where the derivative is 0. Well, we got two cases. Either our max and min are at the points a and b, so that the whole function is a constant function, because your max and min can't get any higher or lower than f of a, which is equal to f of b, so we're done. Otherwise, whatever your function looks like, it has a maximizer or a minimizer somewhere in between. In which case, the derivative at that point is 0 using this lemma. In either case, we found a point such that the derivative at that point is 0. A point in the open interval a, b. Make sense? Okay. So now we're ready to prove the mean value theorem. And the mean value theorem is exactly what we started out drawing the picture for. So that's what we're proving now. So proof of mean value theorem. So let f be a function on a closed interval a, b to r such that f is continuous, I assume. Oh, I just wrote it out. Oh, that's because I already have it here. Such that f is continuous and on AB is differentiable. Two, let m equal f of b minus f of a all over b minus a, and let g from AB to R by g of x is equal to f of x minus mx. Okay, so here's the main idea with the mean value theorem. So with the mean value theorem, I've got some function that starts at f of a, does whatever it does, ends at f of b, right? And I'm trying to find a point in the middle where the slope is the average slope between these 2 points, right? So I'm going to create a new function over here, g of x. How am I going to make g of x? I'm going to basically rotate this function so that f of a and f of b have the same height. And then the average slope between f of a and f of b is going to be 0. And so using this function, they'll have the same height. I know there'll be somewhere where the derivative's 0, where the derivative's 0 after we rotate it is going to be the same thing where the derivative's m before we rotate it. That's kind of like what we're doing here. So, 3. Observe that g of a is equal to f of a. Oops. So when I plug a into g, we get f of a minus m, we'll write out m, f of b minus f of a all over b minus a times a, right? That's what f of a, or g of a is. And I need to show that this just comes out to whatever it comes out to is the same thing as g of b. I need to show that g of a and g of b are the same thing, therefore the derivative of this function is 0 somewhere. Make sense? So let's see. Observe g of a is equal to that, and let me write down what g of b is equal to, and then see if we can come up with a good way to see that they're the same. And g of b is equal to f of b minus f of b minus f of a all over b minus a times b. is equal to, so I'll get everything over b minus a and distribute it through that a. So first I need to multiply this thing top and bottom by b minus a. So I have b times f of a minus a times f of a. So that's taking this and multiplying it by this. I'll write the denominator second. I'm going to write them all over the same denominator. And then I need a minus a times f of b. And then I need a minus is plus a times f of a. And this is all over b minus a. You with me on the algebra? Okay. So now, and g of b, let's expand it out. G of b is equal to b times f of b minus a times f of b minus b times f of b plus b times f of a, all over b minus a. Let's see if I did the algebra right there. So I did b times f of b minus a times f of b minus b times f of b plus b times f of a. Okay, that's right. And let's simplify both these. So here I have the a and the f of a go out. So I get b times f of a minus a times f of b. So in the numerator I'm left with b times f of a minus a times f of b over b minus a. And same thing here. This b goes out with this, so I'm going to write this term first. This is equal to b times f of a. Should be a parenthesis there. B times f of a minus this term, a times f of b, all over b minus a. So they're equal. And that's equal to that, which gives me g of a is equal to g of b. You follow that? So then that's equal to that, maybe put and here, and that's equal to that, which gives me that those two are equal. Okay, so now I know that g of a is equal to g of b. So now I know that there exists x naught such that g prime at x naught is equal to 0. This theorem says if f of a is equal to f of b, the derivative is 0 somewhere in between. G of a is equal to g of b, the derivative 0 somewhere in between.
Do we need to show that g of x is also continuous and differentiable on the open interval inside?
So notice that this function is always continuous and differentiable because it's just a polynomial. And then we knew the conditions under which this was continuous and differentiable. So this is going to be continuous and differentiable on the same domain. So yeah, probably would have been good to specify that here. So, and let you by that, note G is continuous and differentiable like F. The same places that F is. Right?
Right.
Everywhere this is continuous, this thing's also continuous. So their sum's going to be continuous. And everywhere this thing's differentiable, this thing's differentiable. Therefore, their sum's going to be differentiable. Remember that continuity and differentiability are just limits. And we know how to take if you know how to take the limit of two things, you're good. The limit of the whole thing is the limit of the individual things when you're adding them together. So there's nothing weird there. Does that make sense? Remember that those are just limits. Something being continuous, that's just a limit. Differentiability, that's just a limit. The difference quotient, the difference quotient. Anyways, where are we? So I know that those are equal. So 5. Then, by theorem 4.17, there exists x naught in the open interval AB such that g prime of x naught is equal to 0. I'm going to write this the other way, such that 0 is equal to g prime of x naught. But what is g prime of x naught?
Is it the same?
What's the derivative of this?
It's f prime of x minus m.
F prime of x naught minus m. What's the derivative of f? F prime, by definition. What's the derivative of a constant times x? Just a constant. What seems weird? You look like we're doing something really wrong. You remember the power rule?
Yeah.
That's all we're using here. M is just a constant, it's just a number. And x, that's our variable. Take the derivative with respect to, we don't specify that here. Take the derivative, and all you're left with is m, well, negative m. So g prime of x naught is equal to this thing, right? Which gives me that what?
F prime of x naught is equal to m.
F prime of x naught is equal to m. Perfect. That's exactly what we were after. F prime of x naught is equal to n. And we're done. So let's go over big picture what we did one more time. So we start out with some function that looks like this. We minused away its average slope over this interval, so I would start and end at the same point like this. That's what we did with the minus mx, where m is the average slope. So then, we have a function like this. We knew that functions like this have a point where their derivative is 0. So this function g had to have a point where its derivative was 0. But g's derivative being 0 happens at the exact same point where f prime of x naught's derivative is m. So we found an x naught in the open interval ab such that the derivative at that point was the same as the average slope m. Make sense?
I think so.
No questions?
I don't know, it's just a little weird. Like when you go over big picture and everything, it makes sense. I'm wondering if I'm getting held up on the last step, but I think I pretty much got it.
The last step, that's... I don't know how to make that filter your intuition anymore.
I mean, it makes sense.
Yeah, because you're just taking a particular limit of a sum of two terms. Take the limit of those two. What's the limit of this? The limit of a sum is the sum of the limits, or the derivative of the sum is the sum of the derivatives. Remember proving that? One of the things we proved is that f plus g prime at x is equal to f prime of x plus g prime of x. That was the first thing we proved, our first major theorem, once we had our definition of a derivative. That's exactly what we're using here. So the derivative of this thing is equal to the derivative of this thing plus the derivative of this thing. If you want to think about that as plus negative m times x.
You can take the derivative of both sides, right? And it's just fine.
Yeah.
Okay.
All right.
I guess that's how you got that in the first place. You took the derivative of g and then.
Yeah, so looking at the equation like this is me taking the derivative of g, and looking at the equation like this is what was given to me from that theorem. So I knew g prime at x naught is equal to 0. I know g prime at any point is always equal to this, so this is equal to 0 at this particular point. Good? All right. So what is next? If f from I to r is differentiable, then f is constant if and only if its derivative is 0. Okay. So, definition first. We've already kind of been using this definition, but now the book makes it explicit, so we'll make it explicit. If I have some function defined on some domain D to R, we call it constant if there exists some real number C such that the function is always equal to C at every point. Exactly what we've always meant by a constant function.
Does D have to be an interval?
Nope, it's just any domain, any arbitrary domain, doesn't matter where it is. So my function could look like this. And be defined on some weird domain.
That's still constant then.
That's still a constant function. Everywhere it gives the same value. Okay. So that's our definition of constant. Now, proving lemma 4.19. Let's see what we got. Let f be a function. Let f be a function defined on an open interval. I is always an open interval to R. Let f from I to R be continuous. This isn't an if and only if. Let me see then. F if it's constant, then the derivative is 0. The derivative being 0 does not imply it's constant. Or does it?
Didn't we just define it as being constant?
Let me see if this should have been an if and only if. What number is that? 4.19. 4.19. Let I be an open interval and suppose that the function f from I to R is differentiable, then f from I to R is constant if and only if. Okay, that's what I thought. This should be an if and only if. Then f is constant. Oh, that's why I had the verbiage there weird. I think I meant to write that. So f is constant if and only if the derivative is 0 everywhere in the open interval. Okay. So 2, let's pick a direction. The case where the function is constant is real easy, so let's do that way first. That's this way. So assume f of x is always equal to c, then obviously f prime of x is equal to 0. We know how to take the derivative of a constant, so we're done. Good with the first way? Okay. So the second way is a more interesting way. Assume f prime of x is always equal to 0. Then I need to show that this function is a constant function. So
We just use our definition.
I need to use, I need to show that everywhere gives the same value. So let's pick a point in there. Let x naught be any point in our interval, comma. Let's see, I take x naught, now I need to grab an arbitrary point. Maybe this is a better way to do it. Let x1 and x2 be any points in our interval. So I'm going to show anytime you grab 2 points in the interval, they have the same value, therefore it's constant. That's how I think is the best way to show this. Does that make sense? No, because I need to find what it is. So I need to pick a point. So let x naught in I and let c equal whatever the height of that point is, f at x naught. So I'll let c be the height at that point, and I'll show every other point has that same height. And therefore every point's equal to c. I think that's the easiest way to do it. Make sense? Let x be some point in I such that equal to x naught. So, then by intermediate value theorem, there exists some point z in, I'll just say between x and x naught, that way I don't need to know which one's bigger and which one's smaller. There exists z between x and x naught such that f prime at z is equal to f of x naught minus f of x all over x naught minus x, right? If I have picked 2 points in my function, x and x naught, then there has to be a point between them whose derivative gives the average slope between those 2 points. Here's the average slope between f of x and f of x naught. So there has to be some point z between them such that the derivative at that point is equal to the average slope between those 2 points.
Aren't we using the mean value theorem and not the intermediate?
Yes. Thank you. Mean value theorem.
Theory,
Sorry. Yes, we're using the whole big idea of what we've been talking about this whole time. Thank you. Sorry, that was probably real confusing. By the mean value theorem, so whatever my function is, I have no clue what my function looks like. Well, we know it's going to be a constant function, but so far, all we know is it's some arbitrary function. I said, okay, x naught is a point such that the height at that point is c. Now I pick some other random point in here, x. Okay, x goes up to that point. Now I know that there has to be some point in between these 2 points. I'm calling it z, such that the derivative at that point is equal to the average slope between these 2 points. That's what the mean value theorem gives us, right? Mean value theorem. The average value theorem.
I do have a question.
What?
I'm not sure if you said it already, but the definition of constant right there,
Uh-huh.
like, it's giving me a different picture than I think is what it's supposed to be. We just draw like a constant function like that.
So, constant function. So what we're saying is that, so I'll start with some function, and let's give it a really awkward domain. Purple's going to be all the points in the domain of this function. My function has those points in the domain, that point, those points, and that point. Right? Really weird function. And let's see it in as crazy a picture as we can draw. So this function, here's D, is the purple points. A function from any domain to R is constant, provided that there is some real number I can find. The real number I'm going to find we're going to call C. C is this real number, it's that height. If there exists some real number C, such that f of x is equal to C at every point in D. So at this point in D, the value of the function is C. At this point in D, the value of the function is C. At this point, the value is C, C, and at all these points it's C, C,
Right.
and so it ultimately ends up looking like that when you plot all the points. Those are all meant to be the same height, no curving up and down. That's a constant function.
That's exactly what I thought.
Yep, it's exactly what we've meant every time we've said constant function. We've been talking about constant functions without ever giving an explicit definition. Now we have an explicit definition. Okay. So, I have 2 points on a differentiable function. So by the mean value theorem, there has to be a point between them, call it z, such that the derivative of z is equal to the average slope between those 2 points. Right?
You have f of x naught minus f prime of x.
That's a comma on the top line.
Oh, sorry.
Let's shift it down, such that f prime of z is equal to f of x minus f of x naught all over x minus x naught. This is just rise over run, just slope. Average slope between those 2 points. So some point between them, the derivative of that point gives us the average slope between those 2 points.
Right.
Good? Now what is f prime of z? 0. By definition, we assume that this function has a derivative 0 everywhere. So, this is equal to 0, which gives us that. Multiply both sides by looking at this half of the equation now. Multiply both sides by x minus x naught. Notice we know x minus x naught is not 0, because those are different points, so we're not dividing by 0, we're good. So that gives me that f of x minus f of x naught is equal to 0, or in other words, f of x is equal to c. You follow that? C is what we called f at x naught. Right here. Let x naught be any point in there, and we'll call the height of that point c. Anything weird?
Sorry, how do we know that it's 0 again?
Kind of weird that we're using x twice here. Maybe when we define up here, we'll use a y.
Okay.
Or probably should just use it as z, since that's what we reference later. Oh, doesn't matter. Follow it?
Yeah.
Okay, and that's it. We're done. So, a function is constant if and only if the derivative is 0.
Wait, sorry. How do we get that f of x equals c?
I'm calling that value c. It's just so that when it's all said and done, I can write f of x equals c to make you feel really good about the fact, okay, that's constant.
Is that f of x or f of x naught?
F of x naught is c by definition.
Right.
Now we showed f of x.
Oh, right.
Maybe
C,
write
right,
one
C,
more
that
step.
makes sense. Okay, yeah.
F of x equal to f of x naught. So f of x is equal to c. So it's equal to c at x naught, and it's equal to c at x. What is x? It's just any point that's not x naught. Good? Okay. So, what's next? Let g from I to r and h from I to r be differentiable, then g and h differ by a constant. Okay, so what it means for two functions to differ by a constant is when you take the difference of their two functions, you get a constant function. So, real concrete example, x cubed plus 7 and x cubed minus 2 differ by a constant, namely 9. Or negative 9, whichever way you do the difference. The point is just a constant when you take their difference.
So are their functions are the two functions always the same distance apart?
Yeah. Take the difference at any 2 points and you get a constant.
They're basically parallel, so to speak.
Yeah.
Kind of.
A weird use of parallel. The distance between them is always the same. Yes. Parallel. Okay. Yeah, that would make like one circle inside of another circle. The two circles are parallel to each other. Sorry. Okay, let's continue. So, I want two functions that are differentiable that differ by a constant. Let's see, which one are we doing? We're proving 4.20. So, let g from I to r and h from I to r be differentiable. Differentiable on their entire domain. Maybe make a note really quick here. You might have noticed that anytime we're talking about a function being continuous, we always define it on a closed domain. And anytime we talk about being differentiable, we're talking about it on an open domain. Why don't I talk about a function being differentiable on a closed domain?
Cause you,
Because A and B aren't always differentiable.
Because if the function ends at that point, and it ends at a sudden point, how do I measure the slope at that point? We typically think about it as a tangent line, so if I have some function starts there, goes along, ends there, there isn't one and only one tangent line I can draw through that point. So the derivative at endpoints is going to be undefined. But if it's an open interval, and then the function goes along and ends without actually including the point, now everywhere I can talk about the derivative. See how it'd be awkward in this picture, but we avoid the awkwardness in this picture? So that's why with our functions, when we're talking about differentiable, we always are using i's, but for continuity, it's fine using the closed interval. In fact, we want the closed interval for continuity because that guarantees us a max and a min. If it's continuous on an open interval, we're not guaranteed a max and a min. In case that's not intuitive, imagine a function that does this.
Right.
Doesn't include that point, doesn't include that point, doesn't have a max, doesn't have a min. Okay. I guess the one I drew already worked. Oh, doesn't matter. Okay, so we've got G and H are differentiable functions defined on the same open interval I, and their codomains just all are. I forgot what we were proving. Then G and H differ by a constant if and only if they have the same derivative everywhere. So, 2, we'll prove the forward case first. I'm going to want to write a function that I use as their difference for both cases, I think. So let's write that first, and then I'll start my cases. 2. Let f of x be the function g of x minus h of x. And notice f of x is going to have the same domain I, because you can plug that into both of those, so we're fine. So it's defined on the same domain, and f of x is going to be differentiable on that domain, right? So note, f prime at x is equal to g prime of x minus h prime of x. It's everywhere differentiable, and we can get its derivative just like that. This is always defined, so that's defined.
And how do we know that because G and H are differentiable?
Yeah, I know G and H are differentiable. F is going to have the same domain as both of them, since they both have the same domain. And f prime of x is going to be the derivative of these two things. These two derivatives are always defined, since these functions are always just differentiable, so this is always defined. So we're good. Okay. So now we'll do the forward case. And that was the functions that differ by a constant, right? So assume the difference of the functions f of x is equal to c. Remember, f of x by definition is the difference of the functions. So assume that the functions only differ by a constant is the same thing as their difference functions equal to c. You go with me writing it this way? Anything weird? Okay, so if f of x is equal to c, what's f prime?
0.
So f prime at x is equal to 0. Well, if f prime of x is equal to 0, f prime of x is equal to 0. So that gives me that g prime of x is equal to h prime of x. You follow that?
Mm-hmm.
Yes.
Anything weird? I think that's a forward case, right? Yeah. So now let's go the other way. Assume g prime of x is equal to h prime of x. Well, if g prime of x is equal to h prime of x, that gives me that f prime of x is what? What?
It's 0.
0!
Is that easy?
F prime of x is equal to the difference of those two things. If that's the same number, x minus x, or a minus a, whatever you want to call it, is always just 0. So f prime of x is 0. But if I know that f prime of x is always 0, then f of x is
Constant.
a constant. So that gives me f of x is equal to c for some c and r. which is what we were trying to show. Their difference function is a constant. They differ by a constant. Make sense? Nothing weird? All right. Definition. Oh, local max and local min. So, intuition first. Let's just draw some random picture. So let's say I've got a function that starts out way off and who knows where, and it does this a couple times, and then shoots down into who knows where. A local max and a local min. This would be a local min, this would be a local max, this would be a local min, this would be a local max. They're maximums if I can find some interval where I block out the rest of the function, just look at that interval, and it would be a max, then we call it a local maximizer. Right? So if I were to come stand right here and stand right there so you can only see that part, and you say, oh, that looks like it's a maximizer of the function.
Does it have to be an open interval?
We're going to use open interval for the definition. No, it doesn't have to be an open interval, because if it happens on a closed interval for some point in between, let's see, what if it was the endpoint? It has to be an open interval so that you're not using the endpoints. Yeah.
Because if it was a closed interval, every point could be.
Yeah, then every point could be. That's a good catch. Yeah, because if we did a closed interval, then that would be a local max. Yep, good catch. Has to be an open interval. Okay, so that's exactly what we're going to say. A point, this is a local min if I can find some interval in the domain such that it's an absolute min on this interval. Now, how am I going to find this interval? If this point right here, we call it x naught, and if I call this distance x naught, if I call the radius of my interval, if you're okay with me saying that, delta. So if I call this distance right here delta, why is delta escaping my mind? Delta. If I call that distance right there delta, then all the points in this interval, if x is in this interval, if x is in, that interval would be x naught minus delta to x naught plus delta, right? This interval is that interval, the interval with radius delta centered at x naught. X being in that interval is the same exact thing as x minus x naught, absolute value less than delta. Don't forget all the way where we started, chapter 1. You good? Okay, so now when we read this definition, I think it'll make perfect sense. A point x naught is a local maximizer of some function if and only if there exists some delta such that any time x is within delta of x naught, f of x is less than or equal to f of x naught. Shoot, we did maximizer in the definition there, and we did minimizer over here. Restart. Come back to the picture, pick a different point. It's the exact same concept, but let's just write it out one more time. So I'm going to call this point x naught, this point x naught, and then over here we have x naught minus delta, and over here we have x naught plus delta. Now notice, I know that f of x naught is a maximizer, or is a max value on this interval, if f of x naught is always greater than or equal to any x in that interval, or f of x in that interval. That's what it means to be the max value, right? So f of x naught is the max value in this interval if f of x naught is greater than or equal to f of x for every x in this interval. Okay, so that's exactly what we're going to say here. A point x naught is a local maximizer of some function from D to R if and only if there exists some delta such that x being within delta of x naught implies f of x, so some point x in here implies f of x is less than or equal to f of x naught, the max. Make sense? And then it would be a local minimizer of it if we flip the inequality here. F of x is greater than or equal to f of x naught. So maximizer, minimizer, same definition, just flip the inequality on this one. Make sense? Any questions on definition of local max, local min? And intuition, if I would have just asked you what you think those points are, you probably would have just guessed it.
Yeah.
Yeah, so very intuitive.
I think we skipped corollary 4.21.
F from I to R is differentiable. Oh, if it is, and the derivative is greater than 0, then F is strictly increasing. Yes, we did. Okay, thank you. So let's go back up now and do this corollary. Proof, we're going to prove corollary 4.21. Okay. So let f be a function from some open interval I to R such that f is differentiable and f prime of x is greater than 0 for all x in the domain. Okay, so we've got some function whose slope is always positive. We're going to prove that means that the function is always increasing, monotonically increasing, strictly monotonically increasing, right? So how do we show that a function is increasing? We need to show that if v is greater than u, then f of v is greater than f of u, right? So, 2. So let u be in the domain such that v is greater than u. Let's see. What is the right way to do this? So I've got 2 points. I know that the derivative is everywhere positive, so I think I'll do a similar thing where there has to be a point between them, call it z, such that the derivative at z is equal to their average slope. Use the fact that the derivative at z is positive to show that f of v is greater than f of u. I think that's my overall strategy. So u and v are 2 points in this function. This function is everywhere differentiable, so that means then there exists some z between, maybe write it this way so it's very clear. There exists some z between u and v such that f prime of z is equal to, I'll write my v first since it's the bigger one, f of v minus f of u all over v minus u. Right?
Why?
Mean value theorem. Anytime I have 2 points on a differentiable function, there exists some point in between them such that the derivative of that point is equal to the average slope between my 2 initial points. Make sense? Since f prime of z, what do we know about f prime of z?
Greater than 0.
It's greater than 0. Since f prime of z is greater than 0, and u minus v is greater than 0, or v minus u, then f of v minus f of u is greater than 0. Which gives me
How did we get that?
f of v is greater than f of u. Look at this. I know this is some positive number, non-zero positive number, and I know this is some non-zero positive number. If this up here were 0, the 0 divided by positive is 0. 0 is not equal to a positive number. If this were negative, then a negative divided by a positive is negative, not positive. So since this is greater than 0 and this is greater than 0, then the numerator up here has to be greater than 0. How do I know that the denominator is greater than 0?
Because of your interval that you...
By definition, v was greater than u. Yeah. So this has to be greater than 0. which means f of v has to be greater than f of u, or plus f of u to both sides of the inequality, right? Which gives us strictly increasing. And we're done. Any questions on that proof? And it makes intuitive sense, right? If the derivative is always positive, if the slope is always positive, the function is always increasing. That's basically what I'm saying here. Okay, let's go over my note. Okay, so back to local minimizer and local maximizer. Notice that if x naught is a local min or a local max, then the derivative is going to be 0 there, right? But the inverse of that statement is not true. Just because the derivative of a function is 0 does not mean that you have a local min or a local max. And our counterexample is looking at the function f equal to x cubed. So if you draw a cubic, it looks like this. Something like that. And the derivative at 0 is 0, but that is not a local min or a local max. So notice, if f of x is equal to x cubed, then f prime of 0 is equal to 2 times 0 cubed is equal to 0. So the derivative is 0. Oops, 3 squared. So the derivative there is 0, but it's not a local min or a local max. The slope starts out positive and it gets smaller and smaller and smaller and smaller and smaller and smaller, and for an instant it's 0. And then it gets bigger and bigger and bigger. Make sense? Okay. So last theorem. Let f from I to r such that f is twice differentiable. Okay, let's make sense of twice differentiable. If a function is twice differentiable, that means you can take the derivative of its derivative.
Can't you do that with most differentiable functions?
It's very common that if you can take the derivative of it once, you can take the derivative of it many times.
Yeah.
Yes. And the majority of the functions you work with, that is the case, like polynomials.
Is there a case where, can you give an example of where you can only take it once, not twice?
The author gave one. I think it was x times the absolute value of x was the counterexample he gave. I can't remember where he said it. But yes, there are functions where you can take the derivative once, but then after taking the derivative, you end up with a sharp function. A function that suddenly has a point in it where the initial function didn't.
Yeah, it's,
You found it?
yeah, it's f of x equals absolute value of x times x.
Absolute value of x times x. For instance, the function f from r to r defined by f of x. Yep. Okay. Wonderful. Why is my computer doing that? Sorry. Okay. So theorem 4.22. Theorem 4.22. Let f be a function from I to r such that f is twice differentiable, and let f prime of x not be 0. Then, if the second derivative at that point is positive, then we have a local minimizer. If the second derivative at that point were negative, we'd have a local maximizer. And if the second derivative was 0, we can't conclude anything.
Interesting.
Huh?
Interesting.
Interesting, yeah. The second derivative of a function we typically call its concavity. So you're used to the derivative of a function gives you the slope. The second derivative of the function gives you concavity. And concave up functions are happy functions, and concave down functions are sad functions.
Why though?
So imagine a function right here and think about its slope.
Okay.
The slope here starts out very down, very negative, right?
Yeah.
If you think about it, you have to move left to right, negative function, negative slope, you fall down, positive functions, positive slope, you have to work your way up. So we're very negative, and we get less negative, less negative, less negative, less negative, less negative. Here, 0. The slope here is 0. Now the slope here gets more and more positive, more and more positive, more and more positive. So the slope is going from a very negative number to a very positive number. The slope is increasing. The change in the slope is increasing. The concavity of the slope is positive. Concavity is the change in slope.
Is the concavity constant?
Depends on how I draw it. So with a parabola, the concavity is a constant. So if you look at a parabola, and notice, sorry, let's finish this picture and then we'll look at it. And notice this, the slope is always decreasing. Starts out very positive, getting less and less and less and less and less. When you get to the other side of the hill, you have a negative derivative. So concave up is positive, second derivative, or the slope is increasing. Concave down is negative concavity, or the slope is decreasing. So I tried to give you a rough picture over here of how these things are related. So I got a function right here. It's concave up, then it's concave down, right? Or concave down, then concave up, sorry. Here's a function. Now let's try and plot its derivative. The slope over here starts out very, very positive, slowly works its way to 0, and then the slope becomes more and more negative until it works its way to 0. So the slope starts out positive, slowly comes to 0, gets pretty negative, starts shallowing out again, gets to 0 again, and gets positive again. So this is the slope, graphing the slope of this function. You with me so far? Now let's graph the concavity of this thing. The concavity of this thing, the slope starts out very negative, right? The slope of this function now starts out very negative. Because this is just the slope of this function, the same way that this is the slope of this function. So now we're just graphing the slope of this function. Slope of this function starts out negative, works its way to 0, and then positive. Starts out negative, works its way to 0, and positive. This is the concavity of this function. Here we're concave down, here we're concave up. Here our concavity is negative, it's 0 somewhere in between right when we switched, and then over here the concavity is positive.
So concavity is just the second differentiation of a function.
Exactly. It's the second derivative of a function.
Did we decide, I can't remember, I feel like we talked about this, but at some point, if you take the derivative enough times, doesn't it become constant
If you have a polynomial function,
for polynomial functions?
yes. If you have something like the sine function, which is a trig function, it's cyclic. The derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of negative sine is negative cosine, the derivative of negative cosine is sine. Repeat.
Does x to the power of 1/2 count as a polynomial?
No.
Okay.
So what about rational functions?
No.
Just polynomials?
Just polynomials. Well, I don't know about just polynomials, but polynomials for sure.
Okay.
Rational functions, some yes, but as a general rule, no. Anyways, so that's concavity. Okay, so what are we proving? We're proving that if I know that the derivative is 0, so I got some point and the slope of that point is 0, and I also know that it's a concave down function. Concave down functions look like frowns. So I know it's 0, and I know that the function's concave down at that point, then it's a local max.
Oh.
Oh, other way. We could have proved that case, but the case I have written over here is, we've got a point at the function, we know the slope there, the tangent line to that point is 0, and I know that the function is concave up. The second derivative is positive, so the function's concave up, then I know at that point is a local min. That's what I'm proving. Right? Yes. Okay, so let's prove that. Proof of theorem 4.22. So let f from I to R such that f double prime of x exists, or it's 2 times differentiable, and let x naught in I such that f prime at x naught is equal to 0.
And f double prime is greater than 0 of x naught, right?
Thank you. And f double prime at that point is a positive number. Okay, so now we're going to prove that this thing is a local minimizer. I'm proving that x naught is a
I know,
local.
but it says if f double prime of x naught is greater than 0, then that point is local minimizer.
Right.
And that's what you have right there. So
That's what we're proving. We can't use it. We're proving that theorem.
Oh, okay. Sorry.
Yeah, that's the theorem we're proving.
I don't know why I'm getting held up on this, but if you take the derivative of f prime of x naught, isn't that 0? Set 0 is a constant.
If you take the derivative of f prime of x naught, at that point, is it 0? Not necessarily. So let's look at the function, just to help your intuition. Let's look at the function. F of x is equal to, I don't know, x to the 4 minus 2x squared. 4x squared. So there's our function. Notice f of x, or f at 2, is equal to 0, right?
I see why it's not going to be equal to 0.
Okay.
I see. It's because it's x naught and not x in general.
Yeah, we're not saying the whole function is, we're just saying at a particular point the value happens to be 0. Because, yeah, one way you can think about it is if I shift the function up or down, it doesn't change the derivative. So I could have shifted it so it wasn't 0 anymore, and this should still have the same slope. Anyways, okay. So I know we got a point, I know its derivative is 0 at that point. I need to prove that f double prime of x naught is, what am I trying to prove? I'm trying to show it's a local minimizer. Okay, so I need to find some interval so that f of x is always less than or equal to f of x naught, right? Local minimizer. So I need to find a delta such that x minus x naught less than delta implies f of x is less than or equal to f of x naught. I think that's a big picture of what we're trying to do. Right?
Because that's the definition of local minimizer, right?
Yes. X naught is a local minimizer of the function if there exists a delta such that this implies, now flip the inequality.
Yeah.
Oh. Minimizer. Okay. Good thing we stopped and looked at that. Okay. Let's see. I know that f prime of x naught is equal to 0. And I know that f double prime at x naught is greater than 0. Sorry, I'm not sure what I'm going to do yet, just kind of think. So I know that the limit as x approaches x naught of f prime of x naught minus f prime of x all over x naught minus x. I know that the derivative of this function at this point is positive. So this is the same thing as f double prime at x naught. And I know that this is greater than 0. You follow that? What does that give me? Maybe come at this from one direction. So if we do x approaches x naught, where x is, we'll start out coming from the left, less than x naught, then that is positive, which gives me that, let's see, so I know that x was less than x naught, so this is a positive number, right? So this has to be a positive number, which means f prime of x naught is greater than f prime at x. How do we know f prime of x naught is 0? So I already know that's 0, so this limit can just be written that way. So I know f prime of x is positive. Are we doing a local minimizer? F prime of x should be negative.
Yeah, we're.
Minimizer, we should be looking at this. Over here, our derivative should be negative. Over here, it should be positive. So I am doing something weird. The limit as x approaches x naught, if we come from the left, this is f prime of x naught, we'll put that back in, minus that. Concave up, the derivative is getting smaller. We're approaching from the left. That's a positive number. This has to be a positive number, so this has to be a positive number. Oh, when we subtract it, we get a positive number. Okay, that gives me f prime of x is less than 0. Right?
No.
This has, so replace this with a 0. F prime at x naught is the same thing as 0. So 0 minus something has to be positive. So this has to be positive. Or so this has to be negative. 0 minus a negative is what gives me a positive. If this was positive, then my numerator would be negative. My numerator has to be positive, so this term has to be negative. Okay. So I know f prime of x is less than 0 when x is less than x naught. Is that going to help me, knowing that the derivative is negative over here and that the derivative is positive over here?
In the book, it does it both ways. It shows both inequalities. F prime of x is greater than 0 and f prime of x is less than 0.
Oh, he relies on an exercise that we have you do. That's why. Okay, so I guess there's an exercise that says if now let's look at what it does. Since f double prime of x naught is equal to that is greater than 0, it follows that there is a delta such that really you leave the whole proof as an exercise to the student. He leaves the hardest part of the proof as an exercise to a student.
That's nice.
So, let's keep playing with it. So, let's see. So, I know that the limit as x approaches x naught gives us a negative derivative. I know over here I've got a positive derivative. So maybe I'll just write that down to help me keep thinking. If we were to look at the limit as x approaches x naught for x naught greater than x, then we would have gotten 0 minus f prime of x over x naught minus x equal to f double prime of x naught is greater than 0. That gives me that f prime of x now is greater than 0. So now I need to use the fact that the derivative is negative here to say that the values are decreasing as we come closer and closer to here, and then that the values are increasing as we get further and further away, and therefore this is going to be a minimum value. Does that make sense? You see big picture how we're going to do that? So far you're good with the idea that we know that our derivative is negative to the left of this point. Here's x naught. This is x naught. Well, x naught's down here somewhere.
Then this is f, or this is f prime?
So right here I have graphed the function f of x.
Okay.
Okay, so far what have we shown? Since I know that the second derivative at this point is positive, and since I know that the derivative of this point is 0,
Because that's given to us.
yeah, so those two things were given to us. Then using these two inequalities, we just barely showed that the derivative to the left of this point is negative, and the derivative to the right of this point is positive.
Okay.
Right?
And we don't know the derivative at that point. Oh, it's 0.
The derivative at the point is 0.
Right.
But the point is, so now that I know that these values are getting smaller and smaller and smaller, basically I've got a strictly decreasing function over here and a strictly increasing function over here. So the value here is going to be my minimizer. All the values coming over here had to be bigger than this value because they're decreasing. All the values over here had to be bigger than the function because they're increasing. Therefore, this has to be the minimum. That's big picture what we're trying to say here, right? So now we know, so let's see. So I need f of x greater than or equal to f of x naught. So I know that the limit now, as x approaches x naught, and will come from the left again. Now we'll just do the actual derivative of the function. So we have f of x naught minus f of x over x naught minus x. So I know that the derivative, when I come from the left, from up here, is less than 0. You follow me there? Up here I showed that the derivative when we approach from the left is 0, and the derivative when we approach from the right is positive. So the derivative when we approach from the left is 0.
Is less than 0?
Is less than 0, thank you. Less than 0, which is going to give me, I know that x naught's bigger than x, so we have positive. So the only way that this is 0 is if this is negative or 0. Less than or equal to 0, right? No, it's less than 0. Okay.
So the top has to be negative.
So the top has to be negative. Does that still help us?
I had an idea on how to prove it.
This is positive, so one sec. Let's do, then we know f of x naught minus f of x is less than 0, which gives me, add f of x to both sides, f of x naught is less than f of x. Okay. Alright, multiply both sides by a positive number, doesn't change that, so that gives me that. Now the other inequality the other inequality, 5, gives me the limit as x approaches x naught if we use x naught greater than, or x naught less than x, of f of x naught minus f of x all over x naught minus x. In this case, I know it's greater than 0. If that is greater than 0, when I multiply both sides by x naught minus x, this is now a negative number, so that's going to flip my inequality. So that gives me f of x naught minus f of x is less than 0. You good with that? This is a negative number. X naught minus x is a negative number, because x naught's less than x. Negative number. Multiply both sides of this inequality by a negative number, flips the sign, which once again gives me f of x naught is less than f of x.
And that's it, right, basically?
Yeah, that's basically it, because we know that that's the limit as x approaches x naught. Since x approaches x naught, then there exists some delta such that for all delta within, maybe write this out. The limit as x approaches x naught is this of some sequence x is logically equivalent to, how can I say this best? Equals x naught is logically equivalent to the limit as n goes to infinity of x of n is equal to x.
Why is that? Why do we need that?
Well, I guess we don't really need it. We can just think about it this way, but I thought if I showed it to you this way, then I was just going to take you back through our definitions all the way. So this is logically equivalent to there exists delta such that let's go back to this. If I know that xn converges to x naught, then what does that mean? It means that for any epsilon, there exists some n such that from that index onwards, this is true.
And you're using you're going to use the epsilon delta criterion instead?
Not epsilon delta criterion, that's for showing that a function is continuous.
Oh yeah.
We're not using that. All we're saying, well, could we use that?
We're trying to show
The function is continuous, therefore for every...
Don't we already know it's continuous?
Yeah, we already know it's continuous. What the last step that we need now is to get our delta. So far, here's what I have. I have that... Oops. We'll draw it over here. So far I have whatever my function looks like. We're talking at some point x naught. Right? What I have so far, here's f of x naught. I have that, I know now that over here, I have some sequence of number x such that when I approach x naught from this side, then f of x is always greater than f of x naught. And I know that I have some other sequence of terms over here, such that as they converge to x naught, maybe we'll call these ones x1s in my second sequence, f of x2 is always greater than f of x naught.
Right.
So I know that for any sequence you choose that converges from the left, that's the case. I know that for any sequence you choose that converges from the right, that's the case.
Okay.
So, since I know that the sequence converges to x naught, then I know that there exists some epsilon that I can place around it, such that these terms are always within epsilon of this thing,
Or delta.
or delta, but then I have to do the same thing for this sequence and then take the minimum of the two displacement to get my overall sequence.
You don't entirely know that f prime of x2 is always greater than f prime of x naught. Like what if the function on the left or the right, whichever one it is, eventually dips down below x naught?
You're saying way over here.
Yeah.
Yeah, so let's draw this out some so that there's no confusion, and let's draw this out some so that there's no confusion. What I know is that for any sequence you pick that starts at the left, it can start clear over here, but it's a sequence that converges to x naught. What can we say? How am I going to get my starting value?
Can you restrict the domain?
Yeah, that's what we're ultimately trying to do. I need to restrict the domain so I get an open interval,
Right.
and so that I don't accidentally get points that are lower on that interval. They need to always be decreasing on this interval. And there should be a way to get that interval knowing that it's the case for the limit. So I need to go from a limit to an interval.
Why can't you just say if another x value gives you f of x naught, then take all of the ones from the right of that, and same if there's one on the right. then take
But there's
those.
infinitely many that give me that.
Like this sine function?
So what if I've got not even a sine function, but a function that's just super, super, super compact? And we're talking about right there. I mean, how do I encode, take the first point to the left that is higher than this, but don't go so far as to also have got one lower than it? That's an awkward statement to encode. It should be simple with the limits that we have here.
Delta last time?
Just use the delta.
Isn't that what we did?
We're used to doing it for, you give me the delta, then I find the index. Here we're doing it the other way.
Well, I mean, you can define delta however you want.
I know that the sequence converges, which means for any delta you give me, I can find an index such that from that index onwards we're in delta, but here we need to do the other way. I know it converges, and so now I need the interval. How do I get the interval?
It's just weird because they use delta in this problem.
Well, they said they make you do all the work. They say
They said
from
there is a, let's see,
they reference an exercise, and in the exercise they want you to prove that if this is the case, that if f prime of x naught minus f of x, the limit as x approaches x naught, this x naught minus x is greater than 0, then that implies that there exists delta such that x minus x naught less than delta gives you f of x is greater than or equal to f of x naught, which is our whole problem. So yeah, we've got this. We're trying to use this to get to this, and we're done. They're saying you do this as an exercise, and then I'll use your exercise right here. So all they do in the proof is get us to this point.
So do we need to just do the exercise?
Right. We need to just do the exercise, but that's what we're trying to do, is figure out how to get that x naught, or that delta. exercise 18, maybe he gives a hint there. Oh, he sets it up differently. So yeah, maybe we'll just do exercise 18.
And it says use exercise 17.
Oh, it says use 17?
No, in 18 it says use exercise 17.
Oh, geez. So this is not trivial at all. So maybe I'm not going to come up with this on the fly.
Yeah.
Shoot.
All right. So I'm not going to come up with this on the fly, I guess. Sorry. But hopefully the intuition for what's going on is there, right?
Yeah.
I just showed that we're always decreasing. We're decreasing on this side. We're increasing this way, but so the values have to always be decreasing. So I've shown that the values are always less than when we take the limits, or as we get arbitrarily close. But I can't figure out how to use that to get my concrete delta. So sorry.
It's okay.
Do exercise 17 and 18. You'll be fine. Or just be like the author. Nah, the rest is left as an exercise to the student. You got it from here. I got you started. Alright, so yeah, sorry about that. And I think that was the last thing that we need to prove. So 17, 18, I doubt I gave you those as homework problems. I need to remember to go and try and solve those and come back with an actual solution. Just don't want to make you have to sit here and watch me when we could be moving on to other things. So that's the end of section 4.3, right? Next week we will be doing 4.4 and 4.5 in one go. And so the week after that we have our test. Now, fair warning for a bunch of stuff that's going to be on the test. Typically I just give you a bunch of homework problems. I'm only going to give you a couple homework problems. Most of your problems are going to be proving the basic rules of derivatives. So be ready to prove those. What do I mean by the basic rules of a derivative? I mean, you better be able to prove that f plus g prime of x is equal to f prime of x plus g prime of x. You better be able to prove that f times g prime of x is equal to f prime of x times g of x plus g prime of x times f of x. You better be able to prove the quotient rule. We have f over g prime of x. That's equal to the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. You better be able to prove the power rule.
G squared of x, or is it g of x squared?
You need to be able to prove the power rule, so if we have x to the n prime, that's equal to n times x to the n minus 1. What am I missing? The inverse rule and the chain rule. So the inverse rule, f inverse prime of y naught is equal to 1 over f prime of x naught, where y naught is f of x naught. The other way that you've seen it, if you don't like that way, you could do x naught here, and here you could do f inverse of x naught, and it's the same thing. And then you also need to be able to prove the chain rule. If I have f composed with g of x, or f of g of x, however you want to think about that, then that's, I think we usually do g of f when we write it. G composed with f, then that's going to be g prime of f of x times f prime of x. And I think that's the big ones.
So we just prove all of those.
I don't know if you prove all of them, but I probably took 4 of them.
4 top? Okay.
I doubt it. So, be ready to prove those. I think the author has proofs for all of them. I don't think any of them were left as exercises.
Yeah, I can beat all of them in class.
And I'm pretty sure that there was a problem on there about finding the tangent line at a point, so don't forget how to do that.
Okay. Do you provide, I suppose we need to know the equation? Like the form to do that in?
If you
Y
give me
equals
the
F.
equation of the tangent line, I'll know that's what I'm seeing.
I'm saying we need to be able to remember the form, how to find a tangent line, essentially. Like you're not gonna have, the tangent line is this line. Does that make sense?
I am going to give you some function and say find the tangent line at the point, blah, 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 and give you a point. Yeah, so 2 weeks to get ready for the test. We only have 2 tests this semester, so
And then the final-
each of these tests are half your grade. Do I give you a final?
Is there not?
I don't know if I have a final, I might just have tests.
that would be so nice, except for it says final on the syllabus. What did you do for the final last year again?
We had COVID last year, so
And so they
we
didn't do
kinda
final.
got shut down. Yeah, I don't have a final.
So we don't have a final in this
Nice.
class?
That's awesome.
If I don't make one, we don't have one. If I make one, we have one.
So are you gonna make one?
I don't have one.
So you're not gonna make one?
I don't know. Since I'm probably never going to use this textbook again, then I'm probably not going to make one. But then again, we probably have a week of class that we need to fill, so may as well make you take a
You
test.
think so?
Think so, yeah, I do think so.
Huh.
I think we'll have 2 weeks,
You do
unless
only have
So you're saying
spring
we're
break.
gonna take an extra long time next week to not have a final?
So we can just split up next week into 2 weeks.
Very good night.
I would have done that if it wasn't so ridiculous. 4.4, we have 2 theorems. That's it,
Mhm.
2. Maybe there's a definition in there, a definition and 2 theorems.
I think
It's
it'll
almost
take
nothing.
3 hours.
And then
Some theorems
the
take
next
a long
one
time.
is just Leibniz notation. There's no new proofs, there's no new material, it's just notation.
Right.
And so, yeah, can't justify taking 2 weeks with all that. But if we have extra time, maybe we can come up with funner things to do.